In this video, we're going to talk about the Diels-Alder reaction. It is named after Otto Diels and Kurt Alder, and they actually received a Nobel Prize for this reaction in 1950. Now the reaction, so just a little tidbit about the reaction, is between a diene and a electron deficient dienophile, which is an alkene. And it always produces a cyclohexene ring. So it's a six-membered ring with a double bond. And it's also called a 4+2 reaction because, or 4+2 cycloaddition, and that's because a ring is formed by the interaction of 4 pi electrons plus 2 pi electrons. And the mechanism is just you take your diene and your dienophile and you draw your 3 electron flow arrows and it makes this cyclohexene ring. Now, there are about 4 different properties, characteristics of this reaction that we need to look at, and that's what the POGIL exercise is going to take us through. So I will go through that PG18 step to show you that. I will go ahead and say this is concerted mechanism. It's one step. It's kind of what happens with a concerted mechanism. And so you're going to see that with the addition of heat and this 4+2 cycloaddition, you also get, if this was a trans or a cis, then this would stay cis. And that's a product of your stereochemistry. So we'll have syn stereochemistry. So, and that's what happens from a concerted. And we're going to talk about that mechanism in these reactions. So let's go ahead and turn to PG18. So Model 1 talks about the Diels-Alder reaction. This is your diene, which is your nucleophile, and then this is your dienophile, which is your electrophile. You add a little bit of heat, and you're going to get your cyclohexene ring product. And it's going to be very important that you number these carbons, and I want you to line it up just like this when you do your reactions. Okay, so let's read question 1. The diene acts as a, did you circle nucleophile? And the dienophile, 1b, the dienophile acts as the electrophile. And remember, you always start with the nucleophile, electron flow arrows to the electrophile. 1c. For the reaction between the diene and the dienophile, indicate which bonds are broken and which bonds are formed. All right, so bonds that are formed are between 1 and 6 and 4 and 5. So formed are sigma bonds in carbon 1 and 6 and 4 and 5, and then you also have a pi bond between 2 and 3. Bonds broken are pi bond 1 and 2, carbon 1, 2, and carbon 3, 4, pi bond carbon 3, 4, and pi bond 5, 6. Draw curved arrows to show the bonds formed and broken. So draw the 3 electron flow arrows, and so we draw the nucleophile to the electrophile. So this is going to go to that carbon 5. This pi bond is going to go to that carbon 1, and then this pi bond is going to go between 2 and 3. So there's your 3 electron flow arrows. It's concerted mechanism. What does concerted mean? It means all the bonds broken and formed at the same time. It's like a concert when you have flutes playing at the same time the drums are. They're all in concert. It says you can also use dotted lines to show this transition state. So we can do that. And so what you would do is you would just draw these dots here to show the bonds being formed and broken. So how many pi electrons are involved in the Diels Alder? There are 6 pi electrons. This is that 4 plus 2 cycloaddition. You should be able to work backwards from the product of the Diels Alder and determine which diene and dienophile were used. So you're going to have to be able to do this. Refer to the numbering of the product in Model 1. What numbers do the carbon atoms of the double bond have? Carbon numbers of the double bond. So in your product, carbons number 2 and number 3 have the carbon-carbon double bond in your product. So if you number this, you'll be able to work backwards easier. Okay, so in the following cyclohexene product, so here you have a number the carbon atoms from the cyclohexane from 1 to 6. So 1, 2, 3, 4, 5, 6. And then you want to put an X through each single bond that was formed in the above compound. So between 1 and 6 and 4 and 5, we put an X there. Disconnect these single bonds and draw the diene and the dienophile used to form your product. So we'll use some retrosynthetic arrows here. Those are retrosynthesis arrows. And now you can do 1, 2, 3, 4. And then you got the 5, 6. Carbon number 5, 6. So disconnect these and form the product. Once your group has reached an agreement on the above questions, draw the diene and the dienophile used to form the following. Okay, so there is your electrophile. This is your diene. Remember, the diene is your nucleophile. And then this is your, so that's your diene. And the dienophile is your electrophile. And then you have another one here. CO2, this is an ester. And you have a double bond there and a double bond there. So the first thing you want to do is you want to number these, just like you've been numbering. So you have 1, 2, 3, 4, 5, 6. You want to put an X through the 1 and the 6 and the 4 and the 5. So now we can draw our retrosynthetic arrows. So here you have 1, 2, 3, 4, and then you can draw your CO2 methyl, CO2 methyl. And so that's a double bond, but keep in mind you got a double bond still there. So this would actually be a triple bond. And since triple bonds are linear, I'm going to redraw this totally. 1, 2, 3. So this is your triple bond. So if you were to work this problem forward, so this is your diene, which is your nucleophile, and then your electrophile in this case is an alkyne. So as long as you have a triple bond, and then so your diene, your nucleophile goes here, that's number 5, 6, and then that gives you your product. Let's do model 2. Model 2. We're dealing with dienes and dienophiles. So now that you know the Diels-Alder reaction and how to draw the mechanism and numbering and working forward and backwards, there's about 4 kind of concepts, properties that you need to learn about the Diels-Alder. And one of these is the dienes and the dienophiles. And that's what this is going to teach you. Because you want to rank how fast a reaction will happen. So your dienes have double bonds, dienes, and your dienophiles are alkenes or alkynes. Okay, so question 3a. What role does the diene play in the Diels-Alder reaction? The diene is your nucleophile. So that means it's going to be electron rich. Based on that role, the diene should be electron rich. 3c. Dienes are, do you see they're conjugated? That's why they're in this chapter. They're conjugated. sp2, 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 sp2. Okay, so you have sp2 carbons. They're conjugated. The dienes shown are all, okay, now this is S-cis. Now what does that mean? S is sigma, and cis means on the same side. So this is a conformation. Now around your sigma bond, the single bond here, you can get rotation. Now this is locked in because it's a ring. And so you see that your double bond here is on the same side of that sigma bond, that sigma. So here you have a sigma bond, and your diene is on the same side. Here, same thing. Now you do get free rotation. You don't get free rotation around the double bond, but these can rotate. Okay, so that this can rotate to this. So this, there's your single bond, your sigma bond, and then now when you look at your alkene, this would be considered S-trans. And S-trans cannot undergo the Diels-Alder. Okay, it has to rotate into the S-cis conformation. And it can do that at room temperature. Okay, here, this one's going to be more locked in because you've got the methyl here, so you're not going to have as fast rotation. This cannot go into S-trans because it's ring. So this is going to be your fastest reacting diene because you need, so one of the requirements is a conjugated diene, right? A diene, and it needs to be in the S-cis conformation. So if I were you on my reaction sheet, I'd write that as a requirement. Okay, question number 4. The geometry of the diene in the Diels-Alder reaction must be in the S-cis conformation. Which of the following dienes are capable of undergoing the Diels-Alder? So go ahead and circle the ones that you think. If they can rotate and get into the S trans or S cis, then yes, you would want to circle them. And let me tell you another thing. When you're setting up your reaction, always do your rotation to put the starting material in the S cis conformation. That will save you a lot of headaches, okay? So so where's your sigma bond here? I think I drew this one wrong. Okay, so here's your sigma bond. As you can see, these are in the trans. And can it rotate? No. Here's your sigma bond. And here's your diene. This one's locked in. This one's going to be fast, isn't it? Okay, so that's S cis. So that one's good. Here, there's your sigma bond. And here is your diene. Now, can this rotate? This can rotate. So if you didn't want to circle it because it's not in the right conformation, that's fine. But you could rotate that into the right conformation because that's what you would have to do on your test. So there's your double bond. Like this one, it can't do it at all. But this one can rotate. Here, this one's not going to be able to do Diels-Alder because there's your sigma bond, and then here you have your diene, but it can rotate, and then when it rotates you have the S cis that you need. Okay, so B, one of the above dienes is not reactive in the Diels-Alder reaction. Which diene would be unreactive and why? And that would be A. And that's because it's locked in, there's no rotation. Compare dienes C and D. Which diene would react faster? And I would choose D. And the reason why I would choose D is I would say that these methyl groups here are electron donating. So these are electron donating groups, the methyl groups. And electron donating groups, so they're pushing electrons into that double bond, and that makes this nucleophile, the diene, more electron rich. So they're going to react faster. Question number 5. Consider the dienophile shown in Model 2. What role does the dienophile play in the Diels-Alder? So we know that's the electrophile. And based on that role, a dienophile should be electron deficient. Okay, so this is another one of those descriptions of the Diels-Alder reaction. So we said already that the diene needs to be in the S conformation. Now we're going to learn about the dienophile. And so 6A, what kind of substituent would enhance the electrophilic nature of the dienophile? So you want electron withdrawing groups. And you need to learn your electron withdrawing groups because you're going to need to know them for next chapter anyway. So electron withdrawing groups actually make the dienophile, the alkene or the alkyne, more electrophilic. 6B, are all the substituents on the dienophile shown in Model 2 electron withdrawing? So you have a nitrile group, you have an ester, and you have a carbonyl. and kind of like an ester. So yes, those are all electron withdrawing. And then it says circle the groups that would be considered electron withdrawing groups. I guess you could circle all of those. The ester, the nitro for sure, the nitrile. The only one that's maybe not would be this one. And the only reason why I say no to this one is because these lone pairs could donate towards the ring, but you do have competing the fact that the oxygen is more electronegative than the carbon. So it's kind of tricky. But I would say it's hard to say between both of those, but the other ones definitely are. All right, so let's look at D. Draw all resonance contributors for the alkene below. Once your group agrees, discuss how these resonance contributors help explain your answer to 6A. So now we're going to understand the why you want electron withdrawing groups on your dieno file. So it has something to do with resonance. You're probably not shocked. Okay, so let's draw the resonance here. This is your ester. An ester is electron withdrawing group. And this is your dienophile. That means it loves a diene. So here, this alkene, these electrons would go here, and then you can draw your resulting resonance structure. Now remember, we have to have conservation of the charge, so overall. And could we draw some more? Yes, we could. So we could draw what if we took these electrons from the alkene and pushed those onto the carbonyl? Make sure you do your double-headed resonance arrows. And when we do this, we're going to see that we get a positive charge on this carbon, and this carbon is carbon number 5 when we do our numbering. This is the reason the electron withdrawing groups will make that carbon number 5 more electrophilic, loving the electrons. Let's go to Model 3 and understand that this Diels-Alder is a concerted reaction, so it's going to be stereospecific syn addition. Model 3. And you see your product here shows both of these esters are on the same side. We show this with our wedges. 7A. In Model 3, label the diene and dienophile. And you always want to do this. So this is your diene, which is your nucleophile. And this is your dienophile. The geometry of the dienophile is, so both those ester groups are on the same side. So cis. As a group, discuss what happens to the geometry of the dienophile as it becomes starting material to the product. So cis stays cis. You have to show that. So syn means it stays the same. And that is a retention of stereochemistry. Trans would stay trans. If a trans substituted diene is reacted with butadiene, what would the orientation of the product be? So it would be trans. So if you start with trans, you're going to end with trans, and you need to show that in your product. So let's work problem number 8. So we have our diene, which is our nucleophile. And now we have our dienophile with our nitrile groups, and this is a trans, and that is your dienophile. And we add the heat, and what you want to do is do 1, 2, 3, 4, 5, 6. Now your electrons are going to go from here to there. You always want to show your electron flow arrows. You're going to draw your 6-membered ring. And this is going to be 1, 2. Now we have a double bond between 2 and 3. This is 3, 4, 5, and 6. And we want to show that we got trans. So that's your product. And you can see that you have a dash and a wedge. And that clearly shows your stereochemistry. Now we want to talk about the stereoselective endo addition of the Diels-Alder reaction. Model 4. Stereoselective. It's an endo addition. Diels-Alder. I'll just write DA. So here we have a diene. This is a great diene because it's locked in and the oxygen donates those electrons. So it's very nucleophilic, and we're going to react this with our dienophile. We have our methyl ester. This is our dienophile. We're going to add some heat. That's what the triangle is. And now, this is going to be fun for you to draw, by the way. You're going to have to draw some of these bicyclo rings. And this is where numbering is going to help you. I think we can draw that a little bit better. All right, so question number 9A. Label diene and dienophile. That's what I want you to do on each one of these. B, number the carbons. So 1, 2, 3, 4, and then here, 1, 2, 3, 4, and then this is 5, and this is 6. And so here's 5, and here's 6. 1, 2, 3, 4, 5, 6. Oh, and this says on here, you see this says endo, which is your major, and then this is exo, which is your minor. And we'll talk about endo and exo. All right, so what is the difference between the endo and the exo? So the difference is the substituent here is endo into the ring. Okay, so you see how it's axial and it's into the ring, whereas here it is exo, meaning out of the ring. And notice that that's your minor, and that's equatorial. So it's equatorial and it's out of the ring. Which product is your major product? The endo is your major product. Draw 2 possible products for the following reaction. So let's do F. And endo is going to be your major. And we're going to show you why here in a minute. All right, so when we always do this, this is your diene, and this is your dienophile. And then if you number these, 1, 2, 3, 4, 5, 6, you draw your electron flow arrows. 3, 4 goes to 5, 5, 6 goes to 1. Then we draw our 6-membered ring. and we do 1, 2, 3, 4, 5, 6. You have a double bond now between 2 and 3. Now keep in mind here, you've got this carbon here between 1 and 4. So 1 and 4. We didn't number it, but it's there. And you see how we put it there? Okay, so that's also the same thing as drawing it like this. And that's what you'd want to do when you want to show axial and equatorial, right? So here's 1, 2, 3, 4, 5, 6, and now you have both of these going CO2 methyl. This would be hydrogen. This would be CO2 methyl and hydrogen here. Okay, so you see both of these esters are on the same side and they're endo. And that's going to be your major product. And you know I'm going to ask for the major product. Your minor product here would be the exo product. Don't forget your double bond between 2 and 3. This would be minor. Now, if you look at your slides in your book, they show some excellent pictures of why that would be. And it's because of the orbital overlap. And showing you the orbital overlap. Let's go back to your first model here with oxygen. And so we have our diene, and then you have your dienophile. Now what happens is you have these unhybridized p orbitals, and they're lining up for this reaction to happen. This actually, your dienophile, will actually slide underneath your diene. And so when this happens, these electrons will line up. And that's how you form that new bond. And when that happens, this portion here that is electron withdrawing group is going to be more attracted to the electrons here. So here you have your diene, which is electron rich, and you have electron withdrawing groups. So they're kind of slightly positive, right? They're electronegative. They attract electrons. So they're going to be electronically attracted to this diene portion, and that drives the whole endo. So you should be able to look at your slides and figure out which Diels Alder dienes would react faster. And the other thing that is not mentioned in your POGL that you'll need to know about the Diels Alder is that you get a 1,4 product. You never get the 1,3. So what do I mean by that? So let's show you just an example of that, and then I'll let you do your additional problems. So let's say you take this compound here. Okay, what would those reaction products be? And what's the major? I'm always going to ask you for your major. Well, you number it. Okay, this is my diene. It's in the cis conformation. This is my dienophile. And so then we're going to do our electron. We're going to number them. 1, 2, 3, 4, 5, 6. And these electrons are going to go here. Those electrons go there. And then we draw our product. And we got the new double bond here. And we got the CN here. And now this is a, you could start here, 1, 2, 3, 4. You could say this is a 1 for a product. Okay, that's good. Okay, that works. Now, what about if you were given, and sapling will probably do this, what if you were given this? You had to turn it around. I mean, you might get um, something like that, right? Plus, and then what would you have to do? You'd have to rotate this to say, okay, now I've got it in the S trans, and then if you do this here, and you say, okay, 1, 2, 3, 4, 5, 6, those electrons go here, these electrons go here, and then you draw your product like this, 1, 2, 3, 4, 5, 6, right? Now I'm going to tell you that doesn't happen, because if this is a 1, then you go counterclockwise, 2, 3. This is a 1, 3 product. And 1, 3 products don't happen. And the reason why is because this is the carbon that should be number 5. Why should that carbon be number 5? Because of resonance, right? So you have the triple bond here, then that's your electron donating. Those electrons go towards the carbon. And so you get your positive there. Okay, so you're going to get a positive on the 5. So what you need to do, if you get something like this, so if you get something like this, you need to go ahead and take that sigma bond and rotate it and line it up so it's in the S cis conformation, and then you need to align your carbon number 5 here. And so then when you do this now, once you switch both of these around and you line them up, then you can do your mechanism. And when you do that, you're going to see that you get 1, 2, 3, the 1, 4 product. And that's going to be your major product, and that'll work. Okay, looking at your additional problems, you need to show your draw your structures, draw your electron flow arrows for your mechanism, show your stereochemistry. 11, you need to show the Diels-Alder product. Oh, the one thing, the Diels-Alder product is really the reason why it became a Nobel Prize winning is because it's used to make steroids. So when you look at problem number 11, you'll see that that's cortisone, and all of a sudden we can make lots of different steroids and using the Diels-Alder. So that was very powerful, and that's why it became a Nobel Prize winner. Also, if you want more Diels-Alder reactions, you have some that on your additional problems in your textbook, and then I've given you instruction video.